guys, it's Miss Miklos, and in today's lecture we are going to be talking about the inverse of a square matrix. So let's go ahead and just look at our definition of what this is. Okay, so it sounds kind of technical, but it says let A be an n by n matrix, so notice the rows and columns are the same, and let I sub n be the n by n identity matrix. If there exists a matrix, and we read this as A inverse, such that, okay, and I just really want to focus on what this is saying right here. It says the matrix times the inverse is going to equal the identity. And we worked with the identity when we used Gauss-Jordan. Our identity for a 2 by 2 is 1, 0, 0, 1. Okay, and when it says, when matrix A has an inverse, we call it invertible. Otherwise, A is called singular. And if it is not a square matrix, there's no way that it can have an inverse. And what we see over here is if they are inverses of each other, the commutative property exists. And we've seen in our previous lesson that the commutative property does not exist for matrix multiplication, so this is kind of a big deal. So we're going to start here. It says we need to show that B is the inverse of A. So to show that B is the inverse of A, we need to show that A times B is I and B times A is also I, because we need to show that it works both ways. So to do A, B first, okay, so that's -1, -1, 2, 1. B is 1, 1, -2, -1. Notice I have a 2 by 2 and a 2 by 2. Since these numbers are the same, we know that we can go ahead and do this. Okay, so A sub 1, 1. And I'm going to go ahead and kind of circle like we did last time, but just to review, A sub 1, 1 means row 1 times column 1. So I'm just going to circle row 1, column 1. So that is going to be equal to -1 times 1 plus 2 times 1, which is 1. Okay, next, I want to find A sub 2, 1. So once again, that means row 2, column 1. So I'm going to go ahead and say row 2 times column 1. And I would get -1 times 1 plus 1 times 1, which is 0. Next, A sub 1, 2. So that means row 1, column 2. So let's go ahead and highlight those. So I have -1 times -2 plus 2 times -1. So I get 2 plus -2, which is 0. Lastly here, I'm going to do A sub 2, 2. So that is going to be row 2 times column 2. So I'm highlighting those again. So I have -1 times -2 plus 1 times -1. So I get 2 plus -1, which is 1. So we have shown here that this, indeed, when we multiply these two, A times B, we do get our identity matrix. Now we also need to show B times A equals the same thing. So B times A would be 1, 1, -2, -1, -1, -1, 2, 1. So once again, I can see that I have a 2 by 2 times a 2 by 2, so it's going to go ahead and work. So let's start with finding A sub 1, 1, which would be row 1 times column 1. So I'm just going to highlight those. So I get 1 times -1 plus -2 times -1, which is -1 plus 2, so 1. Now I'm going to do A sub 2, 1. So that means I'm doing row 2 times column 1. So I have 1 times -1 plus -1 times -1, which gives me 0. A sub 1, 2 means that I am doing row 1 times column 2. So I would do 1 times 2 plus negative 2 times 1, and I get 0. And then lastly, A sub 2, 2 means row 2, column 2. So 1 times 2 plus negative 1 times 1 gives us 1. So we can see here that I went ahead and got that identity matrix doing A times B and also doing B times A. So that's how we verify or prove that two matrices are inverses of each other. Now we're going to go ahead and figure out how can we actually find the inverse of a matrix. So for 2 by 2 matrices, a simple formula can be used to find the inverse. We can also use Gauss-Jordan elimination. Doesn't that sound fun? Okay, but for 2 by 2, we're going to use this, and this following formula can only be used for 2 by 2 matrices. Okay, so if A is a 2 by 2 matrix given by A equals A, B, C, D, then A is invertible if and only if AD minus BC is not equal to 0. Okay, so our formula here, and I'll teach you guys the other way as well, so it really will be up to you as to what you want to do. This formula, though, it says A inverse equals 1 over this value right here, AD minus BC, is what we call the determinant. And we'll kind of see how we figure that out, and we're going to use that a lot in our last lesson of this chapter. So we're going to do AD, oops, there we go. Okay, we're going to do A times D minus B times C. You guys may remember, and here's like a little preview. It's Mr. Determifish, and he says subtract, baby, so that's why we subtract there. Anyways, then times, we're going to switch these two entries. So notice normally it's A and D. We're going to switch those two and take the opposite values of those two. So if this is the method that you like, and honestly, like the actual work itself is going to be super easy, but it requires memorization. Okay, so for number 2, it says, if possible, find the inverse of each matrix. So what we're going to do here, I'm going to go ahead and just write a little note to myself and remind myself A is 3, B is negative 2, C is negative 1, D is 2. So to find the inverse, we know it is 1 over whatever we find the determinant to be times the matrix. I'm going to switch these two terms, so I'm going to write 2 and 3, and then I'm taking the opposite of these two values, so it's going to become 2 and 1. Okay, to find the determinant, I'm starting up here, 3 times 2, so I'm multiplying across that diagonal, and then Mr. Determifish says, subtract, baby. So I'm writing minus, and then I'm doing negative 1 times negative 2. So you guys can kind of see why we say this is Mr. Determifish, because it looks like a Jesus fish. There we go. Subtract, baby. He just likes saying baby because it's funny. And it makes you remember it. But regardless, this is our method. This is what finding a determinant is. So I have 6 minus 2, so I get 4. Now we know that if I am multiplying a constant or a scalar by a matrix, I am just distributing it. So 1/4 times 2 is 1/2. 1/4 times 2 is 1/2. 1/4 times 1 is 1/4. 1/4 times 3 is 3/4. So we would say that A inverse is equal to 1/2, 1/2, 1/4, 3/4. If we really wanted to see if that worked, we could always then multiply A times A inverse and see if it gives us our identity matrix. Okay, for B, once again, I'm going to start by doing 3 times 2 minus, because Mr. Determifish says, subtract, baby, negative 1 times negative 6. I end up getting 0 here, and the fact that I get 0 tells me that there is no possible inverse. Okay, and that's going to happen sometimes, and this looks like a perfectly normal matrix, but there's no possible inverse for this problem. The reason why getting 0 would be an issue is because when I do 1 divided by 0, we know that nothing is going to work. Last but not least here, part C. So I'm going to do 3 times 5. Mr. Determifish says, I hope you all shouted it at home, subtract, baby. Or for some of you out at the lunch tables, you know who I'm talking to. Okay, 2 times 7. So I have 15 minus 14, which is 1. So I would say the inverse of C equals 1 over, we found that that determinant was 1, so I'm putting that in there. To write our new matrix, I'm switching 3 and 5. And then I'm taking the opposite values of 2 and 7, so -7, -2. So when I distribute 1 to that, I get that C inverse is equal to 5, -7, -2, 3. Okay, so that is one method of finding the inverse of a 2 by 2. And quite honestly, it's pretty simple when we have our notes out. It gets a little bit tougher if we have to memorize that. So now we're going to go into the second method, which is using our favorite Gauss-Jordan elimination. So to find the inverse of A, we can adjoin, which basically means join, the identity matrix to the coefficient matrix. So we have A and then our identity. And we can use our row operations to make it so that we have the identity on the left side. Whatever we're left with on the right side is going to be our inverse. Okay, so let's go ahead and get into this. So I already wrote this out for us. So notice, we're starting with the actual matrix, and on the right side, I have my identity. So my goal is to make this look like this side. So we learned we always start in column 1, and we start with our 1s first. I'm good there, so I'm going to leave that. 1, 4, 1, 0. Now to make this into a 0, I'm thinking I should do row 1 plus row 2. 1 plus -1 is 0. 4 plus -3 is 1. 1 plus 0 is 1. 0 plus 1 is 1. And who said Gauss-Jordan elimination was not useful? You guys weren't thinking about the inverses. Okay, so moving on here. Now I'm moving on to column 2. I already have a 1 here, so I'm good. So I need to make this into a 0. So I'm going to go ahead and rewrite out that second row because that's good to go. And I'm thinking to get rid of this 4, I could do -4 times row 2 plus row 1. So off to the side, I'm going to write -4 times row 2 just because that helps me out, and I get 0, -4, -4, -4. So 0 plus 1 is 1. -4 plus 4 is 0. -4 plus 1 is -3. -4 times 0, not times 0, sorry, -4 plus 0 is -4. So if we look at this, and I'm going to look at this whole problem, notice we have transformed our matrix A into our identity matrix. Where our identity matrix previously was is now our inverse. So I'm going to go ahead and write A inverse equals -3, 1, -4, 1. Okay, so quite honestly, I don't care how you guys find the inverse. If you're really good at memorizing, I think that first method is probably easier for you. If you just want to stick with what we know, then we can use Gauss-Jordan, and here's a new application for it. Okay? Final thing we're going to learn is how can we use an inverse of a matrix to solve a system of equations. And I know you guys are just dying to find another way to solve equations, and I am going to grant your wish today. I'm making dreams come true here. So, as we've already learned, a system of linear equations can have exactly one solution, infinitely many solutions, or no solution. If the coefficient matrix A of a square system is invertible, which remember that means has a has an inverse, then the system has a unique solution defined as follows. A times x equals b has a unique solution given by x equals A inverse times b. And that seems kind of strange. So I think it's going to be easier when we get into example 1 to break this down. So remember that multiplication is not commutative. So it's really important that we do things in the right order here. So first thing that we're going to do here, it says A times x equals b. So we're going to go ahead and kind of set that up and show you guys what that's talking about. So I'm going to write A. Okay, matrix A is going to be -1, 1, 2, -3. That is coming from these coefficients. Okay, that is our coefficient matrix. We talked about that terminology earlier in this chapter. X are our variables, x and y. Okay, and it does go in this order, and if we look, -1 times x plus 2 times y gives us this equation. And it is equal to what we call b. b is our constant matrix. So I have my coefficients, my variables, my constants. So what we want to do here, we want to set it up so it is A inverse times b is going to give us what x is equal to. Okay, we already know that b is -1, 6. I have no clue what this inverse is. And we know x is going to be our solutions. So what we need to do here is we need to start by finding this inverse. And you guys can use whatever method you want. I'm going to go ahead and use that determinant method. So A inverse equals 1 over, so -1 times -3 minus 2 times 1. So let's write that just off to the side. -1 times -3 minus 2 times 1. So I get 3 minus 2, which is 1. Matrix A, we learned we need to switch these two terms. So I have -3 and -1. And take the opposite of these two terms. So I have -1 and -2. So when I distribute the 1, I get -3, -1, -2, -1. So what we're going to do over here, that's what I'm putting in for A inverse. Okay, so I have -3, -2, -1, -1 there. So if we look at this, we have a 2 by 2 matrix times a 2 by 1 matrix. So the fact that these are the same means that we can multiply, and our answer should be a 2 by 1, which means I'm going to have my solutions x and y. So I'm going to start by finding A sub 1, 1. So A sub 1, 1, row 1 times column 1. So -3 times -1 plus -2 times 6. So I get 3 plus -12, which is -9. Okay, next thing I want to find is A sub 2, 1. So this means that I am doing row 2 times column 1. So I have -1 times -1 plus -1 times 6. So this time I get 1 minus 6, or -5. So that tells me that my solution is -9, -5. Now if we substitute that back in, the opposite of -9 is 9. 9 plus -10 is -1. -9 plus 15 is 6. So it does work in both of those equations. So this is just another method, and quite honestly, it can kind of be a pain if it's just given to us like this, but if I'm already given the inverse, this can be a really quick method to solve a system. So we're going to practice this one more time here. Okay, so if we look at example 2, once again it says use an inverse matrix to solve the system of linear equations. I'm going to practice that other method to find the inverse just to make sure that we are understanding how to do that. But first I need to write this as 1, 2 negative 2, negative 3. So remember that's A. X is xy equals B, which is 0, 3. So I'm going to go ahead and try and find the inverse, and I'm going to write matrix A and then write our identity matrix. So this is good. I already have a 1 here. So I know that that first row is good to go. To get rid of this 2, I'm thinking I could do negative 2 times row 1 plus row 2. So off to the side, I'm going to do negative 2 times row 1, which would be negative 2, positive 4, negative 2, 0. Negative 2 plus 2 is 0. 4 plus negative 3 is 1. Negative 2 plus 0 is negative 2. 0 plus 1 is 1. Now, moving on to column 2, I already have a 1, so I need to make this negative 2 into a 0. So I'm thinking we should do 2 times row 2 plus row 1. So 2 times row 2 would be 0, 2, negative 4, because that's a negative there. It didn't show up great, and 2. So 0 plus 1 is 1. 2 plus negative 2 is 0. Negative 4 plus 1 is negative 3. 2 plus 0 is 2. So on the left side now, I have my identity matrix. So this tells me that our inverse is negative 3, negative 2, 2, 1. And on the notes that I have out from last year, I actually used the other method last time, and I got the same exact 1. Okay, so this is the inverse. It doesn't matter how we do it. Okay, so now what I need to do, I need to set up the inverse, which we just said is negative 3, negative 2, 2, 1, times B, which is 0, 3, equals X. So I'm going to start with finding A sub 1, 1. So row 1 times column 1. Negative 3 times 0 plus 2 times 3 is 6. Now I need to find A sub 2, 1. So I'm going to go ahead and do row 2 times column 1. Negative 2 times 0 plus 1 times 3 gives us 3. So that tells us that 6, 3 is our solution. So just kind of to recap the things that we've learned today, we've learned how to verify if two matrices are inverses by using matrix multiplication, and their product should give us the identity matrix. Second thing we learned how to find a 2 by 2 identity just by using the determinant and using that formula that you guys need to memorize. Third thing we learned how to use Gauss-Jordan elimination to give us the identity. I'm sorry, not the identity, to give us the inverse. And then lastly, we learned how to actually solve a system of equations using the inverse. Notice that even though our book deals with 3 by 3s and some higher order square matrices, for your sake, we're only going to focus on 2 by 2s. So if you know how to do 2 by 2s, you're in good shape.